We now need to move into our last type of confidence intervals for Chapter 9. Don't worry, there'll be more in Chapter 11, but this is the last one that's for now. And those are the confidence intervals for population variance and standard deviation. And I say and because really the two formulas are going to be very much tied together. They go hand in hand because all the variances is the square of the standard deviation. So if you have one, you kind of have the other. All right, now you want to make a confidence interval estimate for the population variance and with the standard deviation because they go together. Just like we did for the proportion in section 9.1 or the mu in section 9.2. But there's a big problem, and that is that the variance is squared, which means it can never be negative, never. That means that a distribution that has negative values, like the z distribution or the t distribution, cannot be used. So we must use something called the chi-square distribution. That's not chi like the t, that's chi, with a hard k sound, right, chi. All right, so let me go back to the z and t distributions real quickly. Right here in section 9.2, we have a z-curve and a t-curve drawn together. And you can see that the z-curve, which is the black curve, has a center at 0, and so does the t-curve. Now the z is the one we get to use for proportion intervals, for the one prop z int. Let me bring up the formula so you can see. See? Right here it has z alpha over 2. And then the t interval uses t alpha over 2. And that all seems fine. But the problem is that they have half their values being negative, on the negative side. And that will never work for standard deviation or variance because they're always positive, always. So we had to create a new distribution called the chi-square distribution. Now let's look at the properties of the chi-square distribution, going back to section 9.3 now. All right, suppose you have a simple random sample of size n taken from a normally distributed population. Right, you can't even get the chi-square distribution unless the distribution that it's coming from is normally distributed. So that has to happen. If that's the case with mean mu and standard deviation sigma, then the distribution of chi-square, which is the statistic we're looking at, and this is the formula for chi-square, it's n minus 1 s squared over sigma squared, follows a chi-square distribution with degrees of freedom n minus 1. Just like the t distribution, it has degrees of freedom right here. All right, so let's look at the chi-square, and I've got a picture of it kind of, I have a couple of them actually drawn down here. One has a degrees of freedom of 5, which is the black one there, and one has degrees of freedom 10, which is that gray one right there. Okay, so all values of chi-square are non-negative. When you look at this graph, it actually stops over here at 0. It doesn't go any further. And that's because you can't have negative values, because if you look at the formula for chi-square, everything is squared, everything is positive. So you'll never get below 0. Right? All values are greater than or equal to 0. This distribution is not symmetric. It's been a while, but we've been working with the z distribution for quite a while, and then the t distribution after that. And both of those were symmetric distributions. There's a line of symmetry going down the middle at mu or at 0, and you can see that they're perfectly matched on either side. But that is not the case with these chi-square distributions. They're actually always right skewed. So they're always skewed. Well, not always, but they tend to be, let me put it that way, tend to be skewed right. I'm going to say tend to be because of something else that's coming up. All right, then the area under the whole curve is 1. Absolutely, these are probability distributions. So the probability rules we learned in chapter 5 are still going to hold, that the whole area, the entire thing, must be 1. The x-axis is still a horizontal asymptote because over here you can see that the black curve, the gray curve, they kind of surf along the x-axis, but they never cross it. They just kind of hover around it. So that means that the x-axis is a horizontal asymptote. So it goes on forever and ever, particularly in the right direction. In the left direction, it's going to stop at 0 and be done. But in the right direction, over in the positive side, it's going to keep going right. And that's why these are skewed right? They're not symmetric. And then last but not least, and this is the important thing, which is why I said tends to be, is that as your sample size increases, your chi-square density curve becomes closer and closer to the z distribution. Now that z distribution is the normal distribution you know and love from section, all of chapter 7 and 8.1 and 9.1, right? The standard normal distribution. So you can see that the gray curve is already looking more normal, if you will, than the black curve. Now, it's not normal, I grant you, but it's looking more normal. And that's because the larger your n is, the more normal, quote unquote, this distribution is. Now, keep in mind, the distribution of the data had to be normal, period, right? So you can't do any of this if your data wasn't normal, your data wasn't normally distributed. But chi-square, the new statistic you make from that data, that's not normal unless n increases and goes higher and higher. All right, now that we understand the properties of the chi-square distribution, we're going to have to take the time to actually find the values for the chi-square distribution. And the notation for this is going to be very similar to what it was for the t distribution and the z distribution, namely that alpha is the area in the tail. But this is going to take us longer than I can finish in this video, so I'm going to stop right here. I'm going to pick up right here in the next video for finding those critical values.